In the previous module, we had introduced the factor analysis model. So, what is the factor analysis? Factor analysis consists of finding a number of factors which explains a given set of variables. So, the number of factors are much less than the number of variables. And we saw that the right hand side of the factor model, there is nothing known on the right hand side. Basically, it is composed of all unknown either variables or constants, where f, the factors and the specific factors are variables, and L is the coefficient matrix of loading, which is primarily a constant. And we made certain assumptions regarding f and epsilon, and we saw that f had a dispersion matrix of I, which is a constant variance, and the dispersion for epsilon was psi. So, the parameters in the model would be the elements of the matrix L and the elements of the diagonal matrix psi. What we will do today is how to estimate the parameters of this model. There are usually two techniques applied. One is the principal component method and the other is the maximum likelihood method. We will be looking at the principal component method in today's lecture. Today we will be looking at the estimation of the parameters of the orthogonal factor model that we introduced in the last class. Remember that the orthogonal factor model was the observation vector x is equal to mu plus L into f plus epsilon, where f consists of the factors which are p in number and much less than the m number of variables that we have. Mu is the mean of the process and L is the loadings of each of these factors onto the corresponding variable. Epsilon are the specific factors or sometimes referred to as the errors. The conditions that we imposed were that f and epsilon should be independent of each other, expectation of f is equal to 0, covariance of f is equal to I, there is a dispersion matrix, expectation of epsilon is equal to 0, and the dispersion matrix for epsilon is psi, which is a diagonal matrix. Now, we saw that this leads to the fact that expectation of x is equal to mu. The variance of x given by sigma is equal to L into L prime plus psi. Now, remember that since we are estimating the parameters, we will have to also we can show that the covariance between x and f is equal to L. So, that the factor loadings primarily gives us the correlation, or the also we can show that the covariance between x and f is equal to L. That is, the factor loadings actually give us the relationship between the factors and the corresponding variables. This measures the covariance between these two. Now, when we look at estimation from this problem, what would we be looking at? Primarily, the model has the parameters in L and in the psi matrix. So, there are p into m parameters in L plus the diagonal elements of the psi matrix, which is m. So, there would be mp plus m parameters that we need to estimate, plus the mu, that is the mean of the process. But then the mean of the process, as is always done, can be obtained from x bar. So, mu hat as always would be x bar, and what we will work with is basically x minus x bar, that is the corrected model, which would be equal to LF plus epsilon. And now we would just be looking at the estimation of the members of the matrix L as well as the diagonal elements of psi. There are two basic methods of estimation. One is referred to as the principal component method and the other is referred to as the maximum likelihood method. Remember that the principal component technique is quite different from what we are doing here, but the method is similar to what we do in principal component, and hence it's referred to as the principal component method. So, let us first look at the principal component method. Now, you know that if sigma is a positive definite matrix with eigenvalues lambda 1, lambda 2, lambda p all positive because it's a positive definite matrix, and with these eigenvalues ordered in the sense that lambda 1 is greater than lambda 2 is greater than lambda 3 and so on and so forth, then we can write sigma as lambda 1 into p1 p1 prime plus lambda 2 into p2 p2 prime plus lambda m into pm pm prime. These pj's, remember, are the eigenvectors corresponding to the eigenvalue lambda j. This breakup is referred to as the spectral decomposition of the positive definite matrix. Now, once we do this spectral decomposition, we can show that we can always write this as the product of two matrices. The first one having columns root over lambda into p1, root over lambda 2 into p2, root over lambda m into pm, and the other one is the transpose of this, which would have the rows as root over lambda 1 p1 prime, root over lambda 2 p2 prime, etc., root over lambda m pm prime. Do this, then we can show that if we take the matrices as L, the first matrix as L, and obviously the second one would be L prime, then we can write sigma as L prime, and this L matrices are at the moment m by m matrices, the same dimension as sigma S. Now, this is a breakup of the nature that we had been looking for, except that we don't have the second component, is the psi component. So, if you look at the variance of x, now we can split it up into two matrices L prime, but for the factor model we had the psi, and the psi is absent here. So, how do you do this? What we do here is that we only consider the first p columns of L, of the given L. That is, instead of the m columns, we look at only p column, the first p. So, now we have a matrix sigma tilde say, which is square root of lambda 1 e1 p1, lambda 2 p2 up to square root of lambda p pp, and the transpose of this matrix. Now, this would give us an L prime, which would be different from what we had before. Now, the last m minus p columns are deleted. But then in this case, of course, there would be, it will not be exactly equal to sigma because we are leaving out some of the columns. So, what we get now is an approximation to sigma. Now, let us pick up the diagonal elements from whatever remains. What remains is sigma minus sigma curve. Okay? And if we pick up the diagonals from that, we use those elements to form the matrix psi. Remember that psi is a diagonal matrix. So, this diagonal actually fits into the diagonal of psi. And what we do is we ignore the off diagonal element. So, we can write psi ii as sigma ii minus summation j equal to 1 to p L I j square for all I equal to 1 to m. And hence, what we have now is that we have a part, the first part which is sigma broken up as L prime, and the second part which is psi, which ignores the off diagonal elements of the remaining columns of the original breakup. And this, you can see, gives us estimate for both L and psi. This is primarily the principal component method of estimating the parameters. You can always do this, but instead of just taking the corrected value of x, that is x minus x bar, you can even standardize the values and then apply the method on it. Now, how good is the fit? Because we have made some approximation and we have left out some of the columns, that is the m minus p columns. So, how good is this approximation in this case? So, to look at that, what we look at basically is referred to as the residual matrix. Mind you, sigma would be estimated from the corresponding sample variance covariance matrix of x, which is S. So, starting with S, we get L prime and psi, estimates of those. So, what we do is we take S minus L hat prime plus psi hat, the estimated values. Remember, this would have the diagonal elements as 0, because from the remaining part we had taken in the diagonal elements and put them into psi, and all the other elements would be small but non-zero in most cases. But then if you look at the sum of squares entries of S minus L hat prime plus psi hat, you can see that this is less than the sum of squared entries of S minus L hat prime. And if you look at that, you can see that we can prove it to be less than equal to the eigenvalues lambda p plus 1 hat square to lambda m hat square. Remaining eigenvalues are small, then obviously their square sums would be small, and hence the sum of squared entries in the residual matrix would be small. So we can say that in general the residual matrix would have very small elements and hence can be ignored. So that is one way that we can fit the factor model. We get the ultimate estimates of both L and of psi. Now, one other thing that we should remember here is that if we look at the contribution of any one of the factors on the sample variance, say the contribution to the ith variable by the first factor is given by Li1 square, or rather by its estimate Li1 hat square. So the contribution to the total sample variance, which is the trace of S given by S11 plus S22 etc. plus SMM from the first factor would be L11 hat square plus L21 hat square etc. plus Lm1 hat square, and you can easily see that this can be written as square root of lambda 1 hat p1 hat prime square root of lambda 1 hat p1 hat, which is equal to lambda 1 hat, because p1 hat prime p1 hat is equal to 1. So the proportion of total variability explained by the first factor would be lambda 1 hat divided by the trace of S, which is the sum of the diagonals of the matrix S. So in general, the proportion of variability explained by the jth factor would be lambda j hat by the sum of the variances of X, and this gives us an idea as to the contribution of the total to the total variability by the factor j. And if we add this up, contribution of the first factor, contribution of the second factor, etc., and if this contribution to the variability becomes very high, say 90% or 95%, then we stop. That's how we actually choose P. We select P such that the contribution assumes a certain proportion. And remember that the eigenvalues are ordered. So we'll start with the first one, go to the second, then to the third, and see how much of the total variability they together account for. And once that is done, we will be able to stop taking into account the amount of variability that we would like to obtain. Now let us look at an example. This example is from a consumer preference study where customers were asked to rate several attributes of a product. The responses were on a 7-point scale, and the attributes gives this correlation matrix. So we have the attributes as taste, good buy for money, flavor, suitable for snack, and provides lots of energy. And you get this correlation matrix. You can see that some of the variables are quite highly correlated, which leads us to believe that there must be some same underlying common factor among these variables. So we can try and do a factor analysis on this. Mind you, in this case we are not doing a factor analysis using the dispersion matrix or the sample variance covariance matrix. We can always standardize the variables and do it on the correlation matrix, which we are going to do here. If you find the eigenvalues of this matrix, let's call this matrix R, which is the estimated population correlation matrix. So this is sample correlation matrix would lead to the first lambda 1 hat value as 2.85. Now if you work with 2.85 out of 5, which is the total variability, because the diagonal in this case is 1 1 1 1 1, this is a total of 5. So it's 2.85 divided by 5, which is a little less than 60%. But if we take the second eigenvalue now, which is lambda 2 hat equal to 1.81, then together the first two eigenvalues contribute 2.85 plus 1.81 divided by 5, that is 93% of the variability. So this would be sufficient to explain the data, and hence we will be sticking to 2 factors only. And then what we do is we get the factor loadings. The factor loadings for taste comes out, this is the first variable, let's call it x1. This comes out to be 0.56 and 0.82 respectively. So we can write x1 as equal to 0.56 f1 plus 0.82 f2. Similarly, the second variable x2, which is goodbye for money, can be written as 0.78 f1 minus 0.53 f2. So this way we can write all the 5 variables in terms of the first 2 factors. And if you compute the square of the LIJs, you will find that the communalities comes out to be 0.98, 0.88, 0.98, 0.89 and 0.93, which are very high indeed. Okay? So we have very high communalities, which means that these 2 factors affect all the variables. There is some commonness between these variables. The specific variances are very small. For the first one, it's almost negligible at 0.02. The second one is 0.12, etc. So there is very little additional information coming in from outside these 2 factors, and we can write the sigma matrix as, or rather the estimated matrix as L, which is now 0.56, 0.78, 0.65, 0.94, 0.80 in the first column, and 0.82 minus 0.53, 0.75 minus 0.10 and minus 0.54 in the second column. We get this L prime hats plus chi hat, which we can adjust as before and get as a diagonal matrix with the specific variances in the diagonals. So this is how we do a factor analysis using the principal component technique. A modified approach to this method is referred to as a principal factor solution, where we start with the factor model again and where we actually correct the diagonal elements. So instead of taking R with the diagonal elements 1 as we did before, we presume some hi square values. Hi square, remember, are the communalities. So we presume some communalities values, put them in the diagonal, and then we have a modified R, which is RR. And from this RR, we actually compute the LRR star prime as before by the principal component technique. Once having got that and having chosen the number of variables, having selected that we are going for P of the principal components, or the P of the first P columns, and deleting the last M minus P columns, we can now get the uniquenesses again as 1 minus summation j equal to 1 to P Lij star square. Now once having got this uniqueness, we have got the factor type of model again, but then we started with an arbitrary h values. So what we do is we correct this h. So now having got this, we have got the L matrix. We can now again compute the communalities from here, get the new communalities, substitute them in the previous model, okay, and then iterate. So you can do an iteration sort of method, which this is similar to what we have done before, but some people prefer to work with this method rather than doing it directly from the principal component itself. A popular choice of A should be 1 minus 1 by the R values, that is the correlation values that we get, which is the basically the diagonal of the R inverse matrix. So, H I star, a common choice for the starting value H I star square is 1 minus 1 by R superscript II, where R superscript II are the diagonal elements of the inverse of the correlation matrix. In today's lecture, we were considering the problem of estimation of the parameters of the factor model. We started with the principal component method and showed how we can estimate the parameters which are the elements of the matrix L as well as the elements of the Chi matrix, which is the variance covariance matrix of epsilon. We also saw a modified version of the principal component method. This is the iterative method which is sometimes used instead of the direct sort of cutting out of the principal component method, which is where we need to cut out the last m minus p. So, there is another method which we can also use. In the next module, we will be discussing the maximum likelihood method of estimating the parameters.